Thank you, Brian, for the introduction. Part of what I'd like to cover today is some things on some of the research that I've had available to myself on pavement thickness tolerances, and we've got some actual data that relates to that. But the scope today is I'd like to talk through how our design professionals design paving, and they use the term minimum thickness, and like to address that. And then we're using a lot in our industry today, GPR testing, ground penetrating radar, and it's got some significant digit considerations that we need to apply to our analysis. And then some of our other presenters are going to introduce the subject and of the concept of slope paving and warp paving in our work, and some definitions. 117 has actually got some proposed definitions for that new type of pavement classification. And then I would like to close in the latter third of my presentation some analysis of some GPR data and how it relates to slope paving and warp paving surfaces, and actually complement some of the future presentations. As any other contractor, I got a presentation with qualifications. We've got a bunch of weasel words here that I created. I narrow my subject matter to privately developed projects, so that we're not looking at something that's in the public sector, but the private sector, so that we've got fire lanes and traffic lanes and a nominal amount of truck traffic, the dumpster truck once or twice a week, and parking areas. We exclude the concept of terminal parking that we see at some of our big distribution centers or public streets or interstates. On the design side of things, we always start our projects out with a soils engineer that does a soil analysis, and we use something like a software like pavement.org, pavementdesigner.org, for example, that goes back to the PCA method, goes back to the OSA research, AASHTO research that occurred in the 50s. And that soils engineer will present recommendations in his documents that'll eventually get followed into the for-construction documents by the civil engineer. The civil engineer may or may not follow the soils engineer recommendations. I've seen civil engineers actually change pavement thicknesses because of traffic situations, and the development of the job changes a little bit, so that the civil engineer has to take those changes into enhancement. But both disciplines will use the term minimum pavement thickness. And this minimum pavement thickness concept goes all the way back to the AASHTO research, where in paving, we don't have our factors of safety that we normally have, say, in a structure that's designed under the reinforced code of 318. And so that's where that term comes in. And these licensed design professionals, we look at our service lives that we have in our industry, and as long as we execute the work properly, the designer is designing for a 20-year service life. And the reality is our service lives are easily 50 or 60 years. The data that I'm presenting here, when you take into account the proper K value and the actual strength of the concrete, the service life exceeds 50 years. So we're presenting some things that might be a little scary to the design professional about pavement tolerances, but the reality is we are merely reporting the existing tolerances that are out there today. The reality is, even though we're using minimum pavement thickness and we're not achieving that technically, the reality is we have great service on our pavements. So pavement thicknesses, the tolerances themselves, those the civil engineer and the soils engineer may or may not address in their documents what the tolerance is. And they casually mention minimum thickness and don't call a lot of attention to it. And the contractors typically will assume, in the industry, we assume that that 6-inch pavement, that we do apply the ACI tolerances. A more sophisticated contractor is going to immediately send in an RFI to confirm that. And sure enough, most design professionals would say, of course, the tolerances apply. Sometimes the specifiers will refer to 117 in their documents, their notes on the drawings. Sometimes they will, but not very often. Sometimes the civil engineer normally won't refer to an ACI document historically, but maybe the structural engineer will refer to 301. And when you refer to 301, you incorporate it into the design, into ACI 117. And when the architect issues his specifications, a lot of times those specs will read that follow 301, which incorporates 117. So in a roundabout ways, we can get into 117, but clearly the RFI. But the only time that minimum thickness requirement is applied to the job is when they're involved with a lawsuit. That typically, the reality is that's the application. As we walk through the design, the tolerance that are in there now that I'm going to present to you today are really judgment tolerances. We don't, in 117, if we look at the history of where these tolerances come, and some of the other speakers will address that, but we're really looking at a judgment that was made 15, 20 years ago on our tolerances we have now. Right now, 117 committee is building a database, finding research, publishing documents so that we can publish what we really have been building. What are the real tolerances? And so we're moving in that direction. So today is very, very important that we build this database and build our tolerances on the reality of what we can really accomplish. We are not in 117 advocating that we change how we design our pavements. We're just recognizing this is how we're actually performing out in the field with our products. Currently 117, 2010 version was updated in 15, and section 12 addresses pavements. And you go to section 12 and it's silent on the subgrade tolerance. It's silent on the thickness tolerance, and apparently assumes that we should be using the slab and grade tolerance, which is in section 4. To help clarify things, ACI Committee 330 is got a specification on pavements and parking lots, and we go to that specification and they hit the nail on the head and then clear as a bell, go to section 454 to get your pavement tolerances, and 454 is the slab on grade tolerance. It tells us how to measure, how we analyze it, how we collect the data, that it's the average, all points have to exceed a -3/8 of the design. In my example, that's going to be, they're going to have to exceed 5 3/8 inches. And each individual test has to exceed a -3/4 inch. In my example, that would be have to exceed 5 1/4 inches. So that helps us see it. In the future, we're updating the new section 8 will be paving. It'll be clear as a bell. I guarantee you that we will address how to measure the thickness and how to analyze it. It'll be using the same process that we have been using now on slab on grade. And we hope to have some new information in there as far as slope paving and warp paving based upon the research you'll see today. And we were also going to look at possibly changing the individual -3/4 minimum, but we're not looking at changing the average thickness. That average 3/8 will maintain that. We have developed on slope paving, the definition that's been balloted is that the finished concrete surface and the corresponding subgrade sheet drains in one plane, one direction, very much like we would a gabled house, just be one plane, one slope. And then the other balloted definition is warp paving. It's when our paving surface has multiple contours of the subgrade and the finished surface. And we're finding that being able to align that point in that subgrade exactly with that point in the paving surface is extremely difficult. And you'll see that in the data today. Looking at pavement thicknesses as it relates to GPR measurements, ground penetrating radar, GPR is not used in 117 as an acceptable method to measure thickness. And that's because 15 years ago when 117 was published and written, GPR was fairly new and the parameters and the equipment was expensive and the experience was limited. But so that's why it ended up as an optional checklist item. But now GPR is a lot more economical. Anybody for a few $1,000s or can even rent a device. It's the size of a Dyson vacuum cleaner. And, but it brings up some issues, you know, how do we measure randomly, which is part of the basis for the slab on grade measurements? How do we analyze these thousands of data points that we collect? And it's easy for someone to hunt and find non-compliance and then develop their run that's going to show that data. And then there's accuracy issues. The STM test procedure does not address accuracy or significant digits. You know, having been an engineer from 50 years ago in college, I will admit that I used my slide rule, but I didn't wear it on my belt. But one of the first things you study is significant digits. So that's important to me as I look at how we measure things. In the case of cores, we measure cores and the STM test is very clear how to measure it, the number of measurements, the average of those measurements, and that we round up or down to the nearest 0.05 inches, which is a little bit less than a 1/16 of an inch. So we know on cores that we're about a 1/16 of an inch. The ASTM for GPR does not tell us to what degree of accuracy we have. And the GPR accuracy range it has to be reconciled with several cores, but the average is about 5%. It could be as extreme as an individual measurement could be off by 10%. So that equates in a 6-inch paving to a 1/4 of an inch. So we go from cores at a 1/16 to GPR at about a 1/4, significant difference there. And when we provide data on GPR to the nearest 100th of an inch, it's a little misleading. But to round up GPR to a 1/4 or to a 1/2 could be misleading too. I tend to use a 1/10 just to have something that's maybe in between the realities. So maybe reality is around a 1/10 for GPR measurements. So I want to give you an example of some data that I was able to acquire on GPR. This is for a traffic lane and parking areas. We did confirm the dielectric constant with cores to calibrate our measurements that we were getting. And with that analysis, the average thickness exceeded the 0.56. And our individual points, though, had to be greater than 5.2. And you'll see in our example that we're able to accomplish the average, sometimes excessively, but the points on the -3/4 results are less. But as we look at specifically the slope paving, and I'm going to hit you with a bunch of data at once. but we had about 473 data points that ranged the thickness from 4.2 to 9 inches. We had one odd one out there, really tall, but our average, and I use the term raw, an unfactored, but our raw average was 5.8 inches, and our raw standard deviation was 0.44. Our modified 117 caps the extreme highs. If I have a 9-inch, I have to reduce that value down to 6 3/4 inches. And so I have the data 5.8 inch with the ACI modified method, and my standard deviation becomes 0.41. So we exceed the 5.6 inches minimum. Individual numbers for the spec that we have currently with the tolerance at -3/4, out of the 473, about 9% of the points did not comply. And if we look at a minus tolerance of 1.25 inches, about 20 points did not comply, so that we had about 96% compliance. And then the minus 1.5 inch tolerance were points, 4 points for a 99% compliance. And the reason I kind of picked those areas is to, if we look at our normal bell curve, our data points fall in those areas, and for good compliance, we're looking at a standard deviation of about two units, or about 1.25 inches. For warp paving, the numbers are a little more wild and crazy. Our averages are about the same, 5.8, 5.7 inches, but our standard deviations are significantly higher. And as we look down in the minus data, all our percentages are significantly higher. And our bell curve shows and reflects that data as well. Our conclusions is, for GPR to become more of a mainstream test method, we need to standardize the significant digits and the accuracy of the measurements. And we need to solve some of the questions on the randomness issue. The licensed design professional needs to clarify what tolerances we should be using, and clarify the minimum design thickness issue. And refer to we need to make sure that we get those into our design documents, that we refer to 117. At the moment, 117 is looking at Section 8 enhancement, to make it very clear that we do cover paving, and that we'll utilize the new research information and the new data that we're getting. And at this point, we're looking at using the two classifications of sloped and warped paving. And as we see with this data, there's a significant difference between sloped and warped paving, which justify those classifications. And what we're seeing today is actually the measurements of reality. As we look at the service life of that pavement section, it actually exceeds 50 years, not the 20-year design life. And we've started means and methods of how can we educate our designers, but our contractors, and let's pay more attention to our subgrade, which is actually driving these tolerances. And as we look at our new tolerances, what should they be? And what should those value be? And where should we go through our compliance? Are we looking for 95% or 100%? And maybe we need to address that in our 117 documents. 100% compliance is possible, but we would need to start increasing our pavement thickness if that's what's desired. And then to emphasize again, we need to standardize the GPR and get rid of some of the subjectivity of GPR, and also address the issues of to what measurement significant digits we should be using. And thank you for your time.